All right. Well, thank you for having me at this conference. It's lovely to be here. So today I'm just going to kind of review a literature. Some of it is my own work, some of it is other people's, on endogenous information acquisition. Mostly I'm going to talk about non-strategic settings, but I'll have a little bit to say about strategic settings, and why that's a little bit different. So tomorrow specifically, I'm going to present a paper with Weiji Zhang on engagement maximization. So we're thinking there about recommender algorithms that are trying to keep people paying attention to the content that they show. And that's a strategic setting where people are receiving information that is being sort of parceled out over time. And so I'm going to tell you about two different things today. The first is people choosing to get their own information. That's what's generally called rational inattention. And then the second is situations where one person is trying to persuade another to do something by providing them information. And there's a big literature there called Bayesian persuasion. And so the engagement maximization I think of as something that lives kind of at the intersection of these two things, but is also kind of its own beast. But if you want to know where I'm coming from, you'll know after this lecture. So as I said, models in which agents choose to acquire their own information are referred to as rational inattention, and I'll talk to you about why that language later. And that's usually in a a non-strategic setting. That is, one person is making a decision. I will also briefly talk to you about a large game setting, or like a Walrasian equilibrium setting, where one person is making a decision. They don't think about how their action impacts others. They're just too small for it to matter. But everyone is in the same boat, and collectively their decisions do matter. And that's the large game aspect of it.
So just to put it in context, like the rational inattention stuff, how is that different from experimental design or survey design, say?
Good. I would, at some level, it's very similar. It comes from a different history, but yeah, let me get to that question later. Then there's models where a sender is providing information to a receiver to persuade them to do something. That's an inherently strategic setting, unless, of course, they agree on what should be done, in which case it's kind of boring. So I'm telling you about that because I want to contrast, next time I talk, what happens when someone is trying to persuade you to do something from what happens where they don't care what you do as long as you keep paying attention to them for as long as possible. And that's what I sort of mean by maximizing engagement. And I want to think about the differences between those two situations. Okay, so unlike the previous talks, I'm going to try to drag you through the whole business. So let's get started. So X is going to be a finite set.
Just slow you down whenever I get confused at least.
No. And so the power set is the relevant filtration here. I'm going to use an example in my next talk, which is a picture of Facebook Marketplace, just because that's the example we picked. I think actually Weiji's spouse might have something to do with Facebook. So that might be where the example is from, but I'm not sure about that. And anyways, I want to think about each X here, the little X in the big X, as something like a list of used cars that I could buy. And so it's a list of the cars that are available, maybe some of their qualities, their age, their mileage, their color, along with prices. But in some settings, I want to think about a continuum of X. Usually the answer is no, you don't. You should reconsider that thought. There's a lot of pain and very little gain from making X a continuum, doing a bunch of measure theory, only to get the same results you would have gotten if you had just thought about a discrete set.
So the X's are lists, and then we have a set of lists.
And X is just a configuration of the universe. So, physicists talk about, I don't know, some quantum state. Probability distributions over that state are like a wave function. This is basically the same kind of thing, but I'm ignoring the rest of the universe except for this Facebook Marketplace. But the point is that each X could be an entire list of cars, each of the colors of those cars, each of the mileage of those cars, each of the prices of those cars, right? That's all in one X. So the X is an abstract object. Yeah.
Quick question. I know it's a side point, but the all pain, no gain. What is the pain and what are?
Well, like I want to talk about an X, not a set of positive measure of X, right? Like I want to say this function is equal, not this function is in an equivalence class that is equul.
But is
like,
there anything substantive we're actually losing, or is it?
No, I don't. My view is no.
Right.
I will say there's a history of going with continua, but then restricting yourself to Gaussian signals.
Right.
And there you really are losing something. There are things, the Gaussian distribution is quite special in many ways. So that is the other popular approach, but I'm going to go with the discrete set here. So some questions are going to be interesting when we just have two states. But most questions, to be properly interesting, will require at least three states. So let's think about P of X as a space of probability measures on these finite sets. So each Q in P of X is a probability distribution. I'm going to think about that as a vector of positive numbers. If the cardinality of X is 2, and then those numbers have to add up to 1. It has to be a probability distribution. That's what I mean by that iota vector. And so what I want you to visualize in the X equals 2 case is that we have a line segment. And in the X equals 3 case, I want you to visualize an equilateral triangle. And we are at some point in that probability simplex. It's the word for that equilateral triangle. And we might pick out different points in it. That's how I want you to visualize these spaces. So A is a set of actions. So, for example, you could buy one of these cars or not. Not might also be an action. You need at least 2 actions to have a choice. So we're going to assume that. There are some things, I'm mostly not going to talk about them, that depend on whether A is more or fewer than X in terms of the number of options. Like I'll say something that maybe is obvious, but generically, if you have like 5 actions and 3 states, 2 of your actions are probably not going to be taken.
So you're going to keep both of those as completely unstructured sets?
Yes. Nothing I will say will depend on any of the details. Now, that's because I'm teaching you the abstract formalism. There's like a huge applied literature where these things have meaning and are actually something. I won't talk about that. So the action is taken by an agent. Agent is the word for someone who takes an action, I guess. And the agent has a utility function. So A is the actions, X is the set. If you tell me which action they take in which state of the world, they get a utility that's a real number. The utility is just an encoding of the preference ranking, right? Utility functions aren't real things. If you multiply them by 2 or add them, that's the same utility function. And we're going to think about situations in which the agent doesn't know what the state is when they take the action. So we're going to want to think about the expected utility. So if you assign probabilities, that's that Q thing. Remember, that's a vector of probabilities to different states X, and then you pick action A. Your expected utility is the sum of the probabilities and the utilities. Okay, so what I'm going to do is assume that the agent maximizes her expected utility. Here I am invoking my privilege as an economist to assume something that I know is not true. So there's a wide variety of reasons to think that people are generally not expected utility maximizers. We're just going to sweep that all under the rug. So we're going with expected utility maximization. And that leads to an indirect utility function, U hat of Q. U hat of Q is, if I have beliefs Q, and I take the best action I can under those beliefs, what is my expected utility? And so we've sort of moved from I have a utility that's based on the action and the state to, if I arrive at these beliefs, this is how happy I will be in expectation. And because we're in the expected utility world, the in expectation part doesn't really matter. That's just how happy you are at that intermediate node. What do we know about you? It's pretty abstract objects, but we do in fact know one thing, which is that it is a convex function defined on a convex set. So what do I mean by that? Well, the space of probability distributions is convex. If I take a linear combination of two of them, I have another probability distribution. Remember, it's still positive, still adds up to 1, still has the right dimensionality. And it turns out that U is convex. And what I mean by that is that I say, okay, if I take Q1 and Q2, and now I think about some average of them, and I think about the action that I can take at the average, I could also take that action at Q1 and Q2. But I could probably do better by re-optimizing at each of the Q1 and Q2. And so in general, I will have a higher utility by re-optimizing at each of my beliefs than I will by just picking the action, which is the best action at the average of those beliefs. And that's what convexity is. So even though I have said nothing about what these actions A and sets X are, I know one thing, which is that this indirect utility function is convex. So as I said, this hat U is how happy am I when I act when holding beliefs Q. So now I'm going to think about probability distributions over probability distributions. So I'm going to imagine that through some random process, we end up at one of these Qs. And then I'm going to think about, well, how happy are we given that random distribution? So convexity tells us something about that. So if I take one of these random distributions pi, and remember that's a probability measure on the probability simplex, and then I take my expected utility under at each Q prime, which is a place I might end up. Oh, I'm sorry, this has a typo. I'm sorry. This should not say U hat. This should just say Q prime. I'm sorry about that, typo. So if the beliefs average to Q0, then my expected utility is higher than if I had just my starting Q0. So I want you to think about this as like a prior belief, and these Q primes as like posterior beliefs. And what this is saying is, because of the convexity of U, I would rather sort of take a random draw over beliefs than take the average of those beliefs.
Just another way of saying black dominance.
We're getting there. That's going to be next. But this is right. This is just Jensen's inequality, right? But yes. Yeah, sorry about the typo. Okay. So we know that we like it when our beliefs randomly evolve. So now imagine that we receive a signal, S, from some finite set. And I'm not going to tell you where, but suppose the agent has a prior over the joint distribution of X and S. So they think that they can compute, given this signal, the posterior likelihood of X, and that's perhaps different than their prior. So Q0 is now the marginal distribution over X under this big prior Q. So let QS be the posterior belief after observing S. And we're going to assume the agent is Bayesian. And now here I'm doing a second thing, which I view as equally, is akin to assuming expected utility, which is actually that there's a bunch of evidence that people are not Bayesian updaters, right? It's hard actually to be a Bayesian updater. Those of you who work on machine learning know this. It's not easy to do Bayes formula. But people apparently also find it difficult. And so I listed one experiment there. Nevertheless, I'm going to assume people are Bayesian updaters. All right, so let's remind ourselves what Bayes' rule is. If we get a signal, and the signal could happen with positive probability under our prior, then our posterior is the probability of both things happening divided by the probability of the signal happening, right? It's PA and B divided by PB is P of A given B. If we receive a signal that we did not think could happen, then we don't really know, actually, what Bayes' rule tells us. There's two ways in which this is annoying. The first way, remember how I said measure theory, all pain, no gain? Here's where the pain happens, right? Lots of things are probability zero. You have to start talking about regular conditional expectations as opposed to just conditional expectations. So it's where the pain comes in. It's even worse, though, in a strategic setting. Like, imagine I'm trying to sell you a car, and I make you an offer that you thought would happen with probability zero. What should you infer about my car is a very tricky question. So Daron Ravid has a nice AER paper from 2020 thinking through that thorny issue in the context of rational inattention. It is not.
That's what all dynamic equilibrium refinements are about, right?
Good. So the issue is very much related to things like sequential equilibrium. I'm not sure I would call that dynamic necessarily. It can come up in a static extensive form game. But you're right. But in rational intention, there's an additional thing, which is that if I'm receiving a signal about what you do, and you do something that I thought was zero probability, what should we assume about the signal that I received? Do I detect your zero probability deviations, or did I forget to monitor for that kind of deviation? That kind of thing starts to matter and creates even more complexity. Yeah.
I don't just assume positive, but the signal.
Well,
at the level of generality.
So when we do single agent decision problems, that's basically what we do. When you start thinking about a game, that's tantamount to assuming that the other player plays a totally mixed strategy. And maybe that is a not bad idea. That's essentially what sequential equilibrium is I'm going to assume you play a mixed strategy, you're going to assume I play a mixed strategy. We sort of take the limits as we're allowed to take our mixing probabilities very low. So that's not a terrible suggestion, but it's not a trivial thing to implement. Good.
But it was just a decision problem.
Yeah, if it's just a decision problem, don't open this can of worms. But of course, we do want to talk about strategic settings. So, and there, the worms exist whether we want them to or not.
Problem for very fundamentally, it doesn't matter on this page. You only care about the things that happened, not the things that could have happened.
Yeah. I mean, okay, good. So now there's also a slightly different thing, which is implicit in that decision problem is that the agent's prior is correct. Occasionally, people might have priors that are incorrect.
It's just dogmatic.
Yeah, or there are behavioral theories. Andre Schleifer was for a while promoting a sort of neglected risks framework, where there are certain events that one assumes are zero probability, but are in fact slightly positive probability. That kind of thing also opens this can of worms. So it's not, yeah, I'll just say this is an interesting issue. We'll set it aside for now, but it matters. Okay, so you expect to receive each signal with a certain probability, and therefore I can take Bayes' rule, which tells you what your posteriors look like, and I can take those signal probabilities and I can multiply them together and add up and figure out what your expected posterior is. And that turns out to be equal to your prior. And that's another way of saying what the title of this slide says, which is that beliefs are Martingales. So when you start with your prior, you cannot expect that your beliefs will update in any particular direction. And so it's worth kind of pausing for a moment. You cannot think in the morning that you will become more optimistic about life later in the day, right? Because then you should just be more optimistic now. That's kind of the intuition. But maybe that's not right? Maybe people have biases such that they can predict changes in their own beliefs, whatever that would mean. the sense in which beliefs are a martingale is under your own beliefs. You cannot predict the changes in your beliefs because otherwise that would mean you thought you were wrong and you would have different beliefs. I, if I have different information than you, might be able to predict in which way your beliefs update. So your beliefs are martingales under the filtration of your own information. They're not martingales under any other filtration necessarily. And that's a generic statement about martingales, right? Martingale under one filtration might not be a martingale under another filtration. But I keep saying the word martingale because it is a clue of how we can take these models, which so far have been like one shot, and think about them dynamically. The M word should get you excited if you do continuous time stuff, because it opens up a whole world of tractability that we didn't have. So that's why I'm highlighting it in this way. Good. The signals, on the other hand, are completely arbitrary. And what I mean by that is that if you tell me what the distribution of your posteriors is, and that distribution has finite support, I can reverse engineer a finite set of signals and a prior that will get you from your prior to your distribution of posteriors. And those signals could be totally arbitrary, right? So there's a famous set of signals, 1f by land, 2f by sea, but that could have been 2f by land, 1f by sea, could have been 2f by land, 3f by sea. If they were flashing lights instead of ringing bells, it could have been red and green, right? Like these labels mean nothing. And so if we as economists are observing agents and we suspect they are receiving information, but we don't know what information they're receiving, it doesn't really make a lot of sense to care a lot about the labels we place on the signals we pretend they receive, because we don't know.
But in the multi-agent case, it very much makes a difference, right? So you need to agree what the signals mean.
Well, no. So in the multi-agent case, we want to talk about the correlation of their posteriors. But if I don't know whether you're receiving red, green, or 1, 2, I shouldn't make too much on the difference between those two sets of labels. And this is why there's an advantage to speaking in priors and posteriors instead of signals. The signals are just an added overhead that you don't need and is often unobservable. Now, there are settings where we absolutely know what signals people are receiving, right? We often say that stock market prices are signals of the information of other traders in the stock market. There I know that price, that number, that is the signal. And it makes sense to talk about it that way. But in a lot of settings, we have no idea what signals someone is receiving. And so we might as well just forget about signals and talk about posteriors.
Isn't there something substantive about saying that at least we're using the same signals, right? Like we talk English or French or whatever, but.
Okay, good. So there is something meaningful to the statement, you and I are looking at the same set of signals. Even if we don't know what those signals are. Like if Arushi is watching us and she doesn't know what signals we're receiving, but she knows they are the same. That is a different economic setting than she's watching us, she doesn't know what signals are receiving, but she knows they're independent. This is essentially the issue we were talking about.
Yes, to speak a language that I don't know, right? Then
well, no, remember, we're talking about you and I receiving the same set of signals. Now, there's a different question, which is, are we equally capable of processing those signals? Right? So if
because you mean the signal.
Good, well, right, we're not at the sending stage yet. Right here, we're all just getting signals from the world. And the question is, are we getting the same signals or different signals?
Sure.
Okay, so given a prior, we can talk about Bayes' plausible information structures, which is basically all of the distributions over possible posteriors that average to that prior. Right? And for any one of those distributions, there is some signal structure that could generate it. So this is the right space to be thinking. And then people use the term Bayes consistency to mean that beliefs must be markers. Okay, so now suppose we have two of these information structures, so distributions over posteriors, and they're consistent with the same prior. And suppose that the support of information structure number 1 is entirely contained within the convex hull of the support of information number 2. Okay, so now I want you to go back to that visualization. Remember how we talked about a line segment in the 2-dimensional case? Number 1 is a narrow bit of that line segment. Number 2 is a wider bit that includes the narrower bit. Okay, now I want you to do the visualization with the triangle. Number 1 is some region, imagine a little circle, inscribed in that triangle. Number 2 is a bigger region that includes the little region, also inscribed in the triangle. In this setting, each of the posteriors under number 1 is a convex combination of the posteriors under number 2. And since we know that our indirect utility function is convex, we know that we are happier getting number 2, at least weakly, than we are getting number 1. Number 2 is better for us. And this is Blackwell monotonicity, right? That number 2 is Blackwell more informative than number 1 if its posteriors lie in the convex hull of the support of the other one. Now, it turns out that not only can you say you would be happier in this situation, but every person with any decision problem would be happier in this situation, right? Because it doesn't really matter what the A's and X's are. If this property is true, it is true for all possible utility functions. We can flip that around. If you give me a utility function, and you tell me this property holds for all possible pi1 and pi2, then first off, I know that that utility function is convex. And then second, I can actually sort of reverse engineer and figure out exactly what the utility function must be up to, again, the usual kind of scale and stuff and shift indeterminacy for some decision problem. Now, a decision problem might involve an infinite number of actions, or it might involve a finite number of actions. But in general, if you tell me you always like more information, that's the same as saying it is as if you value information as if you were making a decision.
The decision problem is not unique, no?
No, not at all. Was there a question?
It's right.
Yeah, here I'm saying,
I do that.
well, when I said for all such pi1 and pi2, I said they had to be the same prior. I didn't say anything about that prior being the same on all comparisons, right? And that's, I think, the sense in which I am saying Blackwell here. But yeah. Okay, so if you want information to help you make a decision, I'm going to use the word instrumental. You have an instrumental motive for information acquisition. For example, going back to this Facebook thing, if you want to choose which car to buy or whether to not buy a car at all, you're acquiring the information because you want to make a decision. But if you already know what action you're going to do, like say not buy a car, and you like information anyways, I'm going to call that a non-instrumental motive for information. So some people might looking at cool cars that they are listed here, even if they cannot buy them, right? They might just enjoy that activity, right? Some people like looking at real estate listings, even though they're not actually in the market for real estate, as either a buyer or a seller. So there are settings. I would argue actually most news falls into this, or politics. Like when you read the newspaper and you follow what's going on with Parliament or with the US government or what have you, it's not really actionable for you, at least in any meaningful direct way. I mean, maybe you're contemplating who to vote for in the next election, but I think you probably already know who you're going to vote for in the next election. I think you're doing it because you like it. So there's clearly motives for information acquisition that are not instrumental.
They don't necessarily have to be convex in the same way.
Excellent. So as long as your non-instrumental motives have this Blackwell order property that more is better, then the U hat can capture both those things. But if they are not like that, if there's particular distributions that you like better than other more informative distributions for your non-instrumental reasons, then all bets are off, right? So you can see why more is better is a very appealing assumption in models. We always make it with utility functions. We never like to talk about people getting satiated because weird stuff starts happening. The same thing is true with information. We always like to assume that people like more information rather than less, because otherwise weird stuff starts happening. But that's not obviously true. Yeah.
How long have the values avoidance, for example?
Yeah. Yeah, so to give you some examples of my own for situations where people choose not to acquire information, people do not like to have the plots of movies spoiled for them, right? That's an example where receiving the information is bad. You choose not to and actively avoid it, perhaps at cost. In a more serious and grim thing, there's a genetic disease known as Huntington's disease, which is a very bad disease, not curable, not really actionable. And there's a genetic test for it. So, someone in their 20s or 30s who has a family history of it can choose to find out, but actually often does not want to, right? So there are settings clearly where people don't want more information. There are also settings where people don't want more of anything else, right? Like preferences do get satiated. That happens sometimes. So we're going to avoid talking about that, but it is sort of lurking in the background. I should say,
Things like information overload, like if I can look at 2 options and I wish to pick, I can look at 50.
well, that is very much in our wheelhouse, right? We're going to think about the costs of acquiring more information, and that's where we're going to stick that idea, right?
But like if you give it to me and then I get stressed out.
Okay, good. So that part is kind of missing from the model. Like if I provide you with more options and this makes your decision more complex and hence worse, that's allowed in the model. The model doesn't have and you feel subjectively unhappier, in addition to the objective fact that you will now make worse decisions, right? Those are kind of hard to separate. I should say being unhappy ex post is totally fine, right? We're not ruling out, you find out information, it's bad news. That's 100% included. What is not included is regretting ever having received the information. Because you'll say, look, it was bad news, but this bad news was coming whether I hit my head in the sand or not. So I don't regret the fact that I chose to get the information.
On that point, one thing that's always sort of bothered me about the model a little bit is that there's no predisposal in the sense, right? As in, ignoring is not free.
Oh, no, sorry. I very much disagree with that. The whole argument, like one of the motives for Blackwell, essentially the proof of Blackwell is in some sense, I am allowed to ignore the information. See, if you give me more information, I can always mentally scramble it in my mind to become less information. So if in my decision problem, I, for whatever reason, preferred less information, I could engineer that mentally myself.
Yeah, sorry, I meant in reality, whereas in the model that's not permitted. Like in the model, it's free to ignore information, but when I open my email, that very much feels not.
Okay, good. Yes. So, yeah, okay. I think you might be right that maybe there are settings where it is worse to receive more information rather than less. Some of that is handled in the model by saying, well, but then you'll make worse decisions because of your information overload, right? So that's very much on the table. But if you're unhappy above and beyond that, the model doesn't capture them. Yeah.
clarifying question.
Yeah.
Also because it reminds me of my coursework. And
Sorry.
well, I've only used toy models since then. Where so non-instrumental defined here is that like something is instrumental only if it makes you change your action.
Ah, good. Okay, so you figured out something, which is going to be true, which is that if information is costly, and a particular piece of information will not change my decision, I will not be willing to pay any costs to receive it. Right? It's only the information that is potentially changing my decision that I would be willing to pay a cost for. Right?
Right. Which incidentally is the argument I was briefly alluding to yesterday about how actually if we say publish statistical information in order to inform policy, you only care about the surprising information that does change decisions, which goes very much against the non-selectivity of statistics.
Exactly. You would not pay for something that told you nothing about your current decision plan. Right?
Just to clarify, then this is, then I should think of this as a static set.
Ah, well, okay. So now there's an interesting question, which is, suppose the decision you're making today is not affected by the information I receive, but you're going to make a decision tomorrow that could be, affected by that. Like, say you're a student, you're studying for a test. The test is tomorrow. Should you acquire information that might help you on the test today? Or should you wait until tomorrow? That's an open and interesting question.
But that also goes back to your point about political or like use of political information and the fact that today I might not be able to do much with it, but 6 months down the line, they're like midterms. So
I mean, my own personal feeling is that my votes and political action have no impact on it whatsoever. I am just one of something like 150 million US voters.
I live in Pennsylvania.
Okay, so you're pivotal. Yeah, I can already tell you who will win in my state. Although I can't tell you who will be the nominee. But yeah, so fair. Yeah. To the extent that you think your political actions matter and affect the world, then yes, you could be acquiring it for instrumental reasons. I submit that that is not the case for most people for any reasonable level of the word effect.
But also we do see collective action in the world in various ways where it might not be individually rational.
Yes, exactly. And that's the kind of thing that is subtly being ruled out. Right. So as I tell you about the model, I want to tell you what kind of baggage it brings along with it. Okay. So we have this set now, the big pie, of all possible information structures that are consistent with our prior. And one of them is going to be received by the agent. Now, there are many models in economics where the information is exogenous, right? Or like, as we were talking about yesterday, the monoculture, maybe you want to compare what happens with this one to what happens with that one. And in those settings, you probably
just in the formalism. So you think of this as a two-stage thing of a prior and then a posterior of the signal. That's fine.
Yeah, right now we're doing that. Later it'll be more.
Why we have the POP.
Yeah. No, the PFP this is a subset of the set of probability measures on probability distributions on state of the world. So X is the state of the world.
Yeah.
P of X is probability distributions over states of the world. Those are our posteriors. Yeah.
The distribution.
Now we're talking about the distribution of posteriors, but where it's a subset of them, the ones that are consistent with our prior.
Yeah.
So in many models, we just get one.
But it's still like just a one-shot signal, basically.
Yeah. Well,
it's just one. It's not a sequence of posteriors.
Said what happens between the time we start at the prior and the time we end at the posterior. So yes, you are free to think about this as one shot, if that's how you prefer. I will sort of later say, actually, maybe we were talking about dynamic models the whole time, but that's for later. So there are many models in economics where it's just exogenous. And usually those models have something more interesting going on with like the set of choices, the actions you might take, like what constraints you might be subject to, what your utility function is. They're less abstract on those dimensions. And so the question of like which action you pick is interesting, right? I mean, we saw examples of this yesterday, right? The question was, how do these firms act given this information structure versus how would they act given that information structure in a context where what they are doing is screening out potential workers? That's an interesting question, right? But at this abstract level, you know, that just is whatever this A function is. And so we're going to start with static endogenous models, where this pi is chosen once by the agent, or someone who has the agent's welfare in mind, and that's called rational inattention. Later, we'll talk about persuasion, which is where one person is choosing the pi, the other person is choosing the action, and they don't totally agree on which action they would like to have taken. But for now, single agent choosing pi.
So the prior is fixed, but I can choose any information structure consistent with that prior.
Yes, for now. I mean, I haven't shown you the whole choice.
Like if you think of this as experimental design, you could run an infinitely sized experiment, for instance. So,
Exactly. Although that might be infinitely costly. So we're adding a cost next. Okay, so if you can choose the pi at no cost, the obvious, without loss of generality thing to do is learn the state of the world through your infinite sequence of experiments. And the model collapses to what you might call full information rational expectations. If you can choose only one pi, then there's not really a choice dimension here. It's just the exogenous information case in the stats. So that's not interesting either. But the interesting case is when you can choose from a subset, right? And there, assuming that the subset doesn't include learn everything, you kind of face some trade-offs about what to learn about. And so you're going to optimally make those trade-offs. You're going to learn about the things that are relevant for the decisions that you're going to make. You're going to ignore the information that is irrelevant. So in that sense, it is rational, but you are ignoring some information. And in that sense, it is inattentive. So this is the origin of the idea of rational inattention. But it's basically the notion that you choose optimally over the set of possible signals available to you, but that isn't the same as knowing the full state of the world. Now, there are two flavors of rational inattention. One is this set-based thing. There's no cost, you just pick from your set. The other is that you can choose any pi you want, but you're subject to a cost. And these two things are equivalent, holding fixed the prior decision problem through the usual kind of duality argument. Basically, you know, if assuming that your choice set is convex, then, you know, it has some kind of support function, which can be interpreted as a Lagrange multiplier, which can be interpreted as a marginal cost, and then you get the other formulation. So the cost and constraint versions of the model are essentially the same for a given decision problem. But once you say, actually, no, your prior changed, so I'm going to now talk about two decision problems with two different priors, or your incentives change, I'm going to talk about two different utility functions, then they stop being equivalent. Like, for example, in the constraint version, if I increase your incentives to acquire information to make a better decision, you can't. You can't get any more information than you were getting. You're already up against your constraint. In the cost version, as your incentives go up, you put in more effort, you acquire more information. So they're different when we talk across problems, even though they're the same for any one given problem. Okay, so what's the history of this? Well, Christensen started this line of work in the 1990s. he won a Nobel Prize, not for this line of work, but for his earlier work on empirical macroeconomics. And he started this work because there's a mismatch between macroeconomic models and data. And so this is a 1998 quote from Chris Sims. Delay and inertia seems to arise even where commensurate adjustment costs are difficult to see.
That's right. Everything you've told us so far is pretty much classic decision theory. Let's go back to the 50s.
Yes. And so what's happening with this cost is the new bit. That's sort of what distinguishes rational inattention from classic decision theory. What was Chris Sims saying? He was saying, I don't think it's actually that hard to change your prices or change your spending or whatever. There are lots of decisions that people make that seem, when we look at macroeconomic aggregates, to respond to news only very slowly. But we can't see why that should be just from adjustment costs. It looks like you could just spend less now if you think a recession is coming, or spend more now if you think a boom is coming. So he said, well, but maybe the problem is that not everyone is paying attention. That is, yes, we economists know that some vital piece of news came out now, the Federal Reserve changed its interest rate or whatnot, but not everyone is paying attention. And maybe that's why some people are slow to react. So he developed this formalism and he said, I'm going to say that the cost of information is defined by something called mutual information. Mutual information is the change in the negative of Shannon's entropy. I want the H here to be convex, not concave. So I'm going to talk about the negative of Shannon's entropy rather than Shannon's entropy.
This is where your finite state space become very much not innocent. It's like definitions of entropy are always relative to some dominating.
Well, I don't think it was ever innocent. And I think those issues about definitions of entropy are exactly the normal issues about measurability and stuff like that.
But I think more than that, right? They're like what I define as a uniform distribution is clear in a finite case. It's not clear, not finite anymore.
No, like, I mean, if you have like a bounded space, it's quite clear, right? There's different notions. Like one thing I could say is X is the real line. A different thing I could say is X is the unit interval.
Sure. But
Those
if you
two are
aware of the unit interval, it's still this.
Yeah. No, even X is the unit interval. There's still sort of measure theory stuff that you have to deal with.
Measure theory. It's like what's the distribution that's maximizing?
It's still the uniform.
But
The uniform is well
scaling, right? The uniform of X is different than the uniform of X squared.
Okay, hold that thought. But for now, it's unambiguous what the uniform of X is.
If it's finite.
If it's finite. What is, no, sorry, even if it's a finite interval or something like that, or the unit ball or something. What's unclear is that X rather than X squared should be the variable that we care about. Right? That is a uniform distribution of X and a uniform distribution of X squared are different distributions. We agree on that.
Yeah, but for a finite set, they're the same. At least the finite positive set if they get slick about one.
That part I think is true in the continuum as well. Well, let's take this offline. But I think you're hinting at something, which is that maybe these X's have meaning, that they're not abstract states that are interchangeable.
I think that's entropy only has meaning if the X's have.
Yes, but this is not a finite versus infinite issue. This is a general issue that is true even in the finite case.
But it's statistical mechanics where entropy comes from.
Excellent. Yes,
It's about the uniform distribution.
Excellent. So in a few slides, I'm going to say entropy is inappropriate for these reasons because it treats states as interchangeable. But we're not there yet.
But in physics, there's an additional meaning and structure that comes from the Hamiltonian dynamics that we don't have here.
That's right. That's right. That we don't have here. Anyways, so Chris said this one will work. It'll work everywhere. There's two versions. There's a constraint version. Your mutual information has to be less than some constant. There's a cost version where you just subtract this from your utility. Now, people said, well, you know, Chris gave some information theoretic reasons for like why mutual information was good, but people weren't sure that they really were relevant for economics. So they started thinking about general cost functions. And a quite general class is the posterior separable cost functions, where the cost is the expected value of a divergence between your prior and your posterior. A divergence is like a distance, but is not necessarily symmetric and doesn't necessarily satisfy the triangle inequality. I'm not going to talk too much about it. There's a subset of those things, which are the uniformly posterior separable things. And those things are just the change in an entropy function. But the H doesn't have to be Shannon's entropy. It could just be some convex function. Or I shouldn't say, it doesn't have to be the negative of Shannon's entropy. It could be any convex function.
It's just to harp on that, basically, if you do that experimental design or survey design, your cost also looks quite different from this.
So that
number of observations or things.
So that's an interesting question, right? Is like in a dynamic setting, is something like this or like this equivalent to a number, the number of experiments you have to do, or the number of surveys you have to run, or something like that? That's a good question. It's not obvious what the answer is, though. Don't presume. So there's some empirical evidence consistent with this. So this has a particular property. I won't tell you what that property is. I will just tell you it has predictions that this general class does not. And there's some evidence consistent with it. There is, however, absolutely no reason to subtract C of pi as opposed to, say, F of C of pi, right? Like utilities don't mean anything. And so there is some notion of elasticity here that this F of C of pi could capture, that the C of pi does not. The subtracting C of pi is a convention. That convention has relatively little meaning in this general form, but it takes on a lot more meaning when you combine it with this. Okay, so you might ask, fine, you've sort of set up this whole framework. Can this model actually match data? And it turns out that that was probably the wrong question. The question you should have been asking is, are there any circumstances in which this model cannot match data? Right? Is this model vacuous? And that's what Kaplan and Dean were thinking about. So they were thinking about state-dependent stochastic choice data. What does that mean? It means we as the experimenters know the state of the world, and we see the probability distribution of the agent choosing each action given each state. So that's a joint probability distribution of actions and states. That's our data. We've run an infinite number of experiments. We have no statistical uncertainty. We know that probability distribution. And then the question is, okay, what can we say about preferences? Like, can we say the agent is rationally inattentive? Can we say they have a particular utility function? This is kind of a classic decision theory question. And there are some things that are implied by rational inattention. There are two things in particular. The first is that if you do this action sometimes and that action other times, you can't do better by switching when you do the two actions. That is, you take the action when it is a good idea, not when it is a bad idea. That's one thing that's implied. That's really implied by utility maximization, right? A different thing that is implied is you can't do better by mixing around your signals.
What does it mean, swapping signals?
It's kind of a complicated condition to describe, but basically, imagine you have a conditional probability of receiving a signal in each state, and you have two different signals, red and green. If you say, I want to receive the green in that state and the red in this state versus the swap.
Not just because the signals themselves are meaningless.
Well, remember the signals have distributions, right? So it's not just like in this state versus that state, but it's the distribution, and the distributions are not meaningless.
There's a different distribution of posteriors.
Yeah, exactly. So it basically has something to do with like rotating your posteriors around in different decision problems. But you have to think about like menus of decision problems and stuff like that. This is things decision theorists like to do. So anyways, there are extremely mild, in my view, restrictions. But apart from that, it's actually very hard to rule out this model. It's a bit like utility maximization in that respect. And so rather than think about it as like a very narrow kind of model, I want you to think about it as a general kind of model for explaining random choice or stochastic choice. And so the notion here is that rational inattention is an alternative to random utility models. So you might be familiar with like that logit preference shock model that IO economists love. It turns out that if you do rational inattention with mutual information, you get the same, essentially, modulo some details, logit preference model. That's this Mateka and McKay paper. So
it's for particular information structure and without thinking about welfare, right?
yes, good. So they have rather different interpretations, right? In the random utility model, if I chose this high fee terrible deal instead of this low fee good deal, it must be because I really love the brand that's ripping me off, right? In the rational intention model, it's because you made a mistake, right? So they have absolutely different welfare implications, but they are observably equivalent.
So I'm just trying to understand the observably equivalent part here.
Meaning,
So we have the state dependence.
meaning given a particular vector of prices and characteristics, your choice probabilities will be the same. And that is also true as you change prices and characteristics. So not only are they
If I can move around your beliefs.
no. If I can manipulate your prior beliefs, they become different. It's a little bit like the cost versus constraint thing earlier, right?
Yeah, that's why I was.
They're equivalent in a class, but that class is not all possible
trying to
perturbations.
design the right experiment that might be.
Yes. Yes, and you might realize that in fact, it's not that people love the high fee bank, it's that they're getting ripped off because they're making mistakes. Yes. What is rejected, that says reject, but rejected, is mutual information. So Sims's original proposal does not have the right prediction for how information acquisition responds to incentives. So Kaplan and Dean also showed that. And that's basically because this like subtract the utility is probably not the right model. Okay, but there's a deeper problem, which is that entropy is wrong for economics for a different reason. And that reason is that the states do have intrinsic meaning in most economic settings. So we were talking about thermodynamics or information theory. In the coding theorems, it doesn't matter what the states mean, only their frequency is relevant. But in economics, numbers have meanings, right? Like some car qualities or prices are closer to each other than others. 20,000 pound car is closer to a 21,000 pound car than it is to a 100,000 pound car. Like 21, 20, and 100 are three different states, but two of them are closer in some sense. And there's ample experimental evidence, which I'll show you one example of, which is that people have a hard time distinguishing things that are close together and an easier time distinguishing things that are further apart. I mean, it sounds almost obvious, but that is what is ruled out by mutual information. And so I, with Mike Woodford, developed this neighborhood-based information costs to kind of address this issue.
But there's kind of really two parts to that statement, right? One is like if I commute things around, the information changes. That's even true for the discrete case.
Yes, this is about the discrete case.
But yeah, but then there's like, I don't know, if I say give you three options and one is like, I don't know, $0, one is 99 cents and $1, it's also discrete, but then it's like the second two are closer, then it's about like a more than the ordinal structure to it, right? So what I'm trying to say is like,
yeah, so like there's an interesting question in the world, which is 99 cents closer to $1 or 0, right? And gas stations have figured out that while it might be closer to $1, it is in some perceptual sense closer to 0 than you might think. And that's why prices are 99 cents or end in 99 cents. So here's kind of the lab evidence. So I'm not really going to explain this. This is from the Scoop and Trevino. But basically, on the x-axis here is like your incentive to do left instead of right. Say you have a 2-action problem go left or go right. And in the left side, you really definitely want to go left. In the right side, you really want to go right. And in the middle, you actually kind of want to do what other people do. This is from a coordination game. And then they have average belief and average action. You don't need to look at the red line. What you should see is that there's this like S curve, right? This is common in psychometric studies. When it's obvious to go left, you go left. This y-axis is like probability of going right. When it's obvious to go right, you go right. In the middle, you have this kind of continuum, and at some point, actually, you change quite quickly, but it's not a step function, right? It's continuous. And so if you want to think about
Nash says step function.
Sorry?
Would Bayes Nash or whatever say it's a step function?
The Bayes Nash. Yes, absolutely. That is the prediction. Sorry, I'm using the wrong question. So what the neighborhood thing gives you versus Shannon is that Shannon's entropy will always say it's a step function. Now the probabilities of going left when you should go left and going right when you should go right depend on the information cost. That's this theta. So you can see like when information is cheap, you make the right decision most of the time. But there's this magic cutoff where your action completely jumps. But if you have a hard time distinguishing between 10, 9, and 11, then you can't do that magic thing. And you get sort of a smooth S curve instead. So that's what this cost function is.
That's curve. In a way, it's nicer to have the jump, right? Started.
Yeah, I mean,
the sim started from.
yeah, there's a sense in which this is clean. This is
sort of
complicated.
like they do that.
Yeah, and that's why Chris Sims has a lot more citations than I do, even though I think mine is more realistic. Realistic isn't always the best, but yes. No, that,
Can you tell us what your cost function is?
there's this neighborhood thing, but I'm not going to show you the details. It's not that interesting. But it captures this idea that it's harder to discriminate nearby states. So why this matters, and then this is the slide I added yesterday. So I have this paper with Jennifer Lau of Columbia on large coordination games. And here, agents can learn their own private signals, they can learn public signals, and they can learn about the actions of others. But as in the thing I just described, they might have difficulty discriminating between nearby signals, right? So even though it's a coordination game, you want to do what others are doing. So think about like a bank run. You want to run if others run, stay if others stay. If 30% of people are running, that's hard to discriminate from 32% of people running, right? And that's the kind of place where these details start to matter. Because if I'm allowed to perfectly discriminate between 30 and 32, then there's going to be a multiplicity of equilibria where we have different coordination cutoffs in these kind of games. Whereas if I am not able to do that, that actually drives us more towards uniqueness.
But with amplification, but without multiplicity.
Sorry?
But you still have some kind of amplification of shocks.
Good, yes. So I'm going to make an assumption. And the assumption is that the economy is constrained efficient under a fixed information structure. So any fixed information structure, this coordination game is constrained efficient. And so that means that the only possible externalities here are related to information choice. What are the results in this setting? Well, there's two. You get non-fundamental volatility if people start looking at the public signals instead of doing their own research. That was sort of the monoculture that we talked about yesterday. When you get that if it's cheaper to look at the public signals than it is to do your own research, right? So if you want to find out what's going on with politics, it's cheaper to read a newspaper or something like that than it is to sort of do your own investigation.
So that's different from herding, or
Well, it sort of looks in practice like the same thing, except, yeah, there's this different thing that can happen, which is that rather than either looking at the public signal or doing your own research, you can watch what other people do and copy them. That's what I would call herding. And inefficiency will arise if and only if it is cheaper to watch what other people do than it is to either look at the public signals or do your own research. But these conditions are different. So you can have a perfectly efficient economy as long as I'm not watching other people, but just looking at public signals. If those signals are cheaper, it's efficient for people to look at them. That's not an inefficiency. Inefficiency comes around when I make my decision by gathering information. You are watching me, but I don't do more research because I know you are watching me.
and it's kind of an assumption if you say it's efficient given the infrastructure.
Yeah, so I mean, this is sort of the theory of the second best issue that we talked about yesterday, right? That is, if I start with an economy that is inefficient, then all of this might make that problem better or worse. And everything is ambiguous. So to get kind of a clear theoretical statement, I want to say, let's start with an economy which is otherwise efficient and ask what can go wrong now that people are acquiring information and choosing their own information. And the answer is that if they choose to get information by watching what other people do, that is a problem. If they choose to get information from sources that are not other people's actions, even if they're common, that's not a problem. However, it does create excess volatility, right? You get a lot more volatility when everyone is going off the same information source than you do when everyone is making independent decisions. It's just that the social planner would also want that. To kind of put it in the language we were using yesterday, I would say monoculture does not create inefficiency, but social learning does.
But like, I guess I don't really know like this finance stuff, but like a background to be think of the externality really coming just from the information. I mean, if I make the bank collapse that you have your money by destroying my money.
Well, in the classic Diamond-Dybvig model, right? There is a good equilibrium and a bad equilibrium, right?
And it's not just about information.
Well, it's very much about information.
I don't know, I'm asking.
Yeah. In the sense that which one of those two informations will prevail. If we all had full information, there are many equilibria. The insight of the global games literature of like Morris and Shin is that once we don't all have the same information, actually that can select an equilibrium. Now, the degree to which that equilibrium is good or bad, it kind of depends on exactly the specification of the model and situation, right? Good. I should say also, there are different things that happen in this model in coordination games where you have strategic complementarity, that is, you want to do what other people are doing, versus situations with strategic substitutability. You want to do not what other people are doing. And so in finance, we have examples of both those things, right? We generally think in the stock market, you want to buy the stocks that other people are not buying because their buying has made those stocks overvalued. You want to be a little contrarian. In a bank run type setting, you want to do what other people are doing because you don't want to be the one holding the bank. So there are examples of both those things. Okay, switching gears a little bit, let's talk about Bayesian persuasion. So it's essentially the same model, but now instead of the agent picking the pie, someone else who we'll call a principal is picking the pie. I should say the Bayesian persuasion literature generally uses the words sender and receiver. I'm going to use the words principal and agent just because that's consistent with the other language that I have been using and will use. But I mean, we all mean the same thing. So the principal wants to maximize something, which is the expected value under the agent's posterior of the principal. Notice the V, not the U, value function, which depends on the action and the state, But notice that the action is chosen by the agent. So that A star of Q prime, that's what the agent will choose to do. The principal doesn't control that. But what the principal does have influence over is what Q prime the agent arrives at. And so in general, if the V is not the same thing as the U, the agents may not be aligned, which means that the principal might want the agent to do something different than what the agent wants to do. I want to talk only about that case, and I'm not going to give you a precise mathematical expression for what alignment means. But I will just say there's some degenerate case here where like you and I both agree on what you should do. And so I don't have to persuade you of anything. We're just going to kind of sweep that aside. This is usually analyzed without an information cost or constraint because we don't need it. It's not to say that it's actually not well motivated. Maybe the principal should not be able to choose any pi they want or should have to pay money for a better pi. But you don't need it because you're not going to fully reveal everything to the agent, because then the agent will do what the agent wants, not what you, the principal, want.
And it's with principal commitment of information structure.
Yeah, we'll talk about that in a second. So this literature originates with Kamenitsa and Genskow, and they have a beautiful paper. You really only need to read the introduction to just lay out what this whole big idea is. I will try to give you my own version of that. So let's stick with the cars example. Our states of the world are two. There's one car for sale, and it has one particular price. And the only thing that's uncertain is that the car might be good or the car might be bad. And there's 50-50 on that under the agent's prior. Now, what the agent can do is either buy the car or pass on the car. And if they buy a good car, they get a utility of 1. If they buy a bad car, they get a utility of -2. And if they pass, they get a utility of 0 no matter what. The principal wants the agent to buy the car. Doesn't care about the quality. So the principal gets a utility of 1 if the agent buys the car, and 0 if the agent does not buy the car. So you can see they are not aligned here, right? The principal wants the agent to buy a bad car. Maybe you've had an experience like this in your life if you've ever gone car shopping. Now, one thing they could do in this setting is that the principal could provide the agent with no information. But you can pretty clearly see, because you get a +1 versus a -2, and you have a 50-50 prior, that if you were the agent and your posterior was equal to your prior, you would not buy the car, right? Absolutely not. But now, suppose I send you a signal, and my signal is going to be that I either recommend the car or I don't recommend the car. And the way this signal works is that I will recommend the car when the car is good 3/4 of the time. And I will not recommend the car when the car is good 1/4 of the time. And similarly, I will recommend the car when the car is bad 1/4 of the time. And I will not recommend the car when the car is bad 3/4 of the time. So my recommendation conveys information about the quality of the car. And you can pretty quickly see that if I do this recommendation, oh, I'm sorry, I said this completely wrong. I'm speaking entirely in terms of posteriors here. Right now, I think the probabilities that I said were in fact correct for this example, but I'm saying they send these signals with the correct frequency such that these are your posteriors. If you think the car is good after a recommendation with 3/4 probability, you will buy it, right? The kind of critical threshold here is 2/3. And so actually now, since I send the unconditional probability of each of these signals is clearly 1/2, I have now gone from you never buy the car to you buy the car half. Right, so by sending you these signals, I can get you to buy the car sometimes. Even though ex ante you probably don't want to. Now, there's a convention that we adopt in this literature, which is that if the agent is indifferent, they will do what the principal wants. And the reason we adopt that is that we like to say there are optimal policies. Otherwise, we have to say there are no optimal policies, but there's like a supervising sequence of policies that nearly achieves. You don't want to be in that business. So you just say, if the agent is indifferent, does what the principal wants.
Convention or delivery.
It's a convention, but every author independently discovers it when they start talking about this and be like, keep saying, there's no optimal policy, but there's a sequence that approximates an optimal policy.
But if just depend on how you define the game, that this is, I mean, you've sort of started with the principle that an agent sort of send and receive the benefits. We specify, we don't say the game that, I mean, there are many games where people are different between things that they
So when we talk about games, there's a question of, can this indifference support this equilibrium? Right, and so the game theoretic way of saying this is there is an equilibrium where when the agent is indifferent, they do what the principal wants. We are restricting ourselves to that class of equilibrium. Right. But yeah, you could justify this as saying the supervising sequence thing does not have an equilibrium technically. And that's why we don't look at it. Okay, so what is the best strategy for the principal? So we have these binary signals, I either recommend or I don't. And I want to maximize the probability of you buying the car. So I want to maximize the probability that I get to send the recommendation signal, which is the probability of your recommendation posterior. And I'm subject to a few constraints. The first is that I need to get you to buy the car when I recommend it. So your recommendation posterior has to place a weight on the good car of at least 2/3. Otherwise, you won't buy the car. I'm also subject to the constraint of Bayes consistency or Bayes plausibility, that the recommendation posterior probability times of G times the probability of that recommendation plus 1 minus that times the G under not recommendation has to be 1/2 because that was your prior. I don't really need to worry about the B state because probabilities add up to 1. And so I can, it's sort of like Walrus law. I can always drop one state and not worry about it. So this is a little optimization problem. And you quickly figure out, okay, I want to make my recommendation just good enough that you follow it, no better. So I'm going to set this probability to 2/3. I want to maximize this, and anything I do to increase the bad state probability of being good just constrains my budget here. So I'm going to make sure that when I tell you no, you know the car is bad. And then I can achieve a probability that I get to recommend the car of 3/4. And this is kind of stunning to me, right? We're in a situation ex ante where half the time you should not buy the car, like for sure. And yet I can get you to buy the car 3/4 of the time by cleverly designing the information structure. And so if you want to know like what was surprising about Kamenitsa and Genskau, like why did it make such a splash? It's that people had the intuition that this could not be, that I could not get you to do something with an unconditional probability that was higher than the unconditional probability that that action was good under your prior by providing you with information, right? Because like here, I actually didn't do any better, right? Like I got you to buy the car half the time you should buy the car. Okay, that doesn't seem so surprising, right? I could have done that with full information. This one though is kind of shocking.
But again, it's commitment, right? So
yeah.
experts that always want to recommend it.
Good. So the persuasion is surprisingly effective, but it does require commitment. 1/4 of the time, I have to not recommend the purchase, even though obviously I always want to recommend the purchase. And so the question is, how do you do this? So like one thing you could do is like hire staff or make an algorithm that you can't change each time, but you can systematically bias towards recommending the purchase. So now this starts to look a little bit like the engagement type stuff that we've been thinking about. Like maybe one way to commit is to design an algorithm rather than individually interact with each user. People used to make the same argument in the context of a bureaucracy. That is like, how is it that the bank commits to not paying you any interest on your savings account, even when you ask? Well, the answer is that the person you ask has no power in the bureaucracy to make that happen for you. That's how the bank committed, right? Like in principle, if you were a very big saver, you could negotiate with the bank president yourself and probably get a good interest rate. But you, as the small individual who deals with this clerk who has no power, the bank is effectively committed to not negotiate. A different interpretation of this is that the principal sets up an experiment, but then the agent observes the experiment. Yet another is that the principal sets up the experiment and the agent observes the setup, so they know what the signal realizations mean. You can also get commitment out of like repeated game type considerations, right? Like maybe, you know, and I think this would probably be relevant for like a car dealer. They suffer a penalty if they really sell you a lemon. So they don't want to do that too often. On the other hand, they don't want to never do it. And this is sort of hinting at what the optimum for the principal is under like a full theorem type result. So there's a very large literature on Bayesian persuasion, and I'm not going to be able to tell you all about it. I will tell you that people have thought quite a bit about this commitment issue. And when you need it, all of these things are papers. In some settings, verifiable disclosure is enough. That is, I don't need to commit to telling you the bad news. I only need to make sure that if there is good news, I can fully and verifiably disclose it to you. That is enough to recover the Bayesian persuasion.
One thing is verifiable disclosure is interesting. I've seen a paper that you actually in the pre-analysis plans. But it's basically pretty general with the structure you get that pre-analysis plans start becoming sensible, right? Which is kind of what we often think, like when you do statistical analysis, you can't verify what you haven't disclosed, but the stuff you do disclose, somebody's going to look at your code.
Yeah, and I guess the point there with the pre-analysis plans would be that they are not committing to writing the paper if it doesn't work. They'll just have filed that pre-analysis plan and it'll stay there in the repository.
In our case, they kind of, once they don't commit to sticking to the pre-analysis plan, but then the pre-analysis plan, because it's sent before you see the data.
Yeah, so I think what this thing would say is actually that even if they only write the paper if the results are good, but they can verifiably disclose the pre-analysis plan, that might be enough to get the Bayesian persuasion outcome.
But then they can send the signal before they see the data, so that's kind of the crucial part.
Yes, exactly. That's enough. Yeah.
This super insightful.
Okay.
But it refreshes stuff that we learned. But the interpretation of this static sort of setting is also, gives you a sense of the repeated game setting. But like, given that this paper was in your school, I was just wondering, is there like a repeated version?
Oh yes, absolutely. Like Amir was editing the JPE for a while, and I think he built like a huge literature through that. There are many papers in the JPE thinking about dynamic Bayesian persuasion. I am not an expert on that. I'm sort of an outsider to it, so I can't really do it justice, but a huge literature thinking through these questions. Okay, but let's switch back to dynamics. So we're going to go back, no more persuasion principle, just agent. But we're now going to think about the possibility that after you get a signal, you get another signal. So you choose your pi, you get some new beliefs. call them Q1 is your posterior. And in the static model, you just sort of choose your action based on Q1. But in a dynamic model, you now get to do one of two things. Stop and do Q1, your action based on Q1, or choose another thing we'll call pi1, receive that signal. Now your posterior is Q2. And so you can repeat this at each time t. Sorry, it says utility there. That should be beliefs, QT. At each time t with beliefs, QT, choose either to stop and act and receive your utility, or keep going and choose another signal structure. So let's start with those UPS cost functions, the ones where it's the expected change in an entropy. And you can see that if I sort of add this up, I keep adding and then subtracting the same intermediate term, at least in expectation. And so the expectation of the cumulative cost is just the expectation in the change of entropy between when I start and when I stop, which is a stopping time, potentially random stopping time tau. So I can just write the agent's problem as maximize my utility subject to a cost. I'm sorry, that should be a clause.
This class cost function is kind of dynamically consistent.
Yes, exactly. And I only really need to think about the distribution of posteriors over which I stop. I don't need to think about the path along the way with this class of cost functions. And so the dynamics sort of don't really matter. Like I could just learn it all at once. I could learn it gradually. Doesn't really matter. Everything here is kind of indeterminate.
This organization, there's no benefit to that. You can't learn something that's going to change my value.
Excellent. Yeah. So what's going on, what's kind of special about this is that the cost of information is, it's not becoming cheaper to get information because I already have some information or something like that.
You do have a stopping time that's adaptive to.
Yeah. The stopping time is adapted to the process of the queue, but there's no sense in which, like, for example, it is better to study ahead of the test so that I can slowly process the information than it is to just cram all the night before.
Right, but then the thing that I said is wrong then, because the stop time is actually adapted to the information that you receive. So the stop time itself is right.
Yeah, it just doesn't matter. Yeah. So I think you said no benefit. Yes. Okay, so let's add some reasons to care. First, let's talk about an opportunity cost of time. And second, let's talk about a discount. And for the discount to make sense, we're going to need to assume the utility is positive. And I'll come back to that. And we're going to treat C as a cost. Then in the presence of these things, the optimal policy is obvious. Gather all the information immediately. Right? If you take time, you just incur these things. Either your utility starts to shrink because of discounting, or you pay the opportunity cost. Just don't do that. If the date of the test is t, you should do nothing until t, and then cram and take the test. Right? That's the conclusion here. Okay. This is obviously not the right model of information acquisition. Like, it is easier to process information slowly over time rather than all at once. So let's go to the constraint version. And in the constraint version, in continuous time, what I want to do is say the change in your entropy function is bounded by some constant chi as the horizon shrinks. I want to say sort of over each little dt, this change is constant. A different way of saying this thing is to say h of q minus chi t is a super martingale. If you're like me, every time you have to think about whether it's super or sub. That is my most frequented page on Wikipedia. So don't feel bad. Okay. The agent's problem is now this guy. So now we have the discounting, our utility. This is our opportunity cost, subject to beliefs being a martingale. Remember, that just comes from Bayes plausibility, and this thing being a super martingale. And then, of course, our belief process and our stopping time have to be in the appropriate domain to avoid technicalities. I'm not really going to talk about that. People who do like continuous time dynamic programming love to talk about admissible policies, but they never really want to tell you exactly what that means because it's a pain. Okay, I'm going to say something which is hopefully obvious, but turns out to be super deep, and this is due to my co-author Weiji. This function e to the negative rho t, where rho is your rate of time preference, is a convex function. And what that means is that you would prefer, if you had to kind of gamble over your stopping time, to either stop right away or very late, rather than at some intermediate time. That's obvious, fine. What does that have to do with anything? Well, it turns out actually it tells you a lot about the nature of the signal you would like to receive. You would like to receive a signal that either immediately and decisively tells you what to do, or tells you nothing, rather than a signal that gives you some information. Because a signal that immediately and decisively tells you what to do or tells you nothing allows you to either stop right now or delays your stopping quite a bit. A signal that tells you some information is sort of like giving you an intermediate stopping time. This is a little bit of a vague intuition. I can tell you it's true.
So it
cannot
like
take it through the math.
that again depends on the cost you have for information acquisition.
Anything in this category. So the only assumption here is that H is convex. So even if you do my neighborhood thing, which I say is the best and greatest thing ever, it's still true.
But again, I don't know, my cramming intuition would be like, I don't know, I can only memorize one fact per day.
Good. Well, so yeah, this doesn't quite get at that, right? Because this says, yes, you gradually study for the test, but it turns out that your studying takes the form of praying for an epiphany, right? Where you suddenly master the subject and otherwise learn nothing. So if there's something weird about this, and I will try to convey what I think is weird about it. So let's consider a different class.
No, that's why we'll be running a bit over time, but
Yeah, let's see.
5 minutes is fine.
Okay, 5 is fine. Okay, I can do this. Let's consider a more general class where we now sort of convexify this thing. In that case, without the discounting, but with the cost of delay, beliefs diffuse. They don't follow a jump thing. You do gradually learn time. And your choice probabilities are the same as if you didn't have this F thing. And that basically the intuition is that with the F being convex, what you want to do is sort of stay in the cheapest part and gradually learn a little bit at each instant. Since we're going slow, I'll say this sort of highlights something quite interesting, which is that if you think about cost of information in a dynamic problem versus a static problem, they maybe should have different properties. So there's a very nice paper by Alex Bludell and Weiji talking a bit about prior invariance. So one thing that you might want in your cost of information is that the cost of running an experiment doesn't depend on your beliefs. That seems very intuitive. That's a static intuition. When you put that as the period cost in a dynamic model, it turns out that your beliefs influence which experiments you will run in the future, which means that sort of the overall cost does depend on your beliefs, even though the cost of each experiment does not. So the way people interpret this is that actually prior invariance is not a desirable property in your one-shot model, if your one-shot model is meant to summarize the complexities of a dynamic problem.
Because of the adaptive stopping.
Yeah. But it's not just about stopping, but about the choice of experiment.
Right, if I commit my information acquisition on the path, that presumably would.
Yeah, what makes this possible is that your choice of experiment in the future can depend on the experiment you run today.
Yeah, so it's different if you run a static RCT versus a bandwidth result.
Okay. Why does the discounting give us such weird things? Well, you may have noticed it requires strictly positive utility. That's usually not words that make sense. Like I should be able to subtract a constant from utilities and get the same answer. And the answer is that there's actually a secret action in these models, which is never stopping. Never stopping implicitly has utility of 0. And so the reason that something might need to be positive or negative is as a comparison between that and never stopping. And so what's going on in the discounting model is that never stopping is getting more and more appealing as time passes relative to choosing an action.
So it's kind of a flavor like the inside option and bargaining.
Yeah, exactly. And so, yeah, very much so. And so that actually kind of messes things up. So just quantitatively, to give you a sense of why I like the opportunity cost instead, suppose you were making a 100,000 pound decision and you had 10 hours to think about it. You have a rate of time preference of 5%. Your discounting over those 10 hours is worth about £6. The average hourly wage in the UK is £20 per hour. So for your 10 hours, your opportunity cost of time is £200. So even though this is, I would say, a pretty high stakes decision, right? £100,000 seems like a lot, much bigger than a lab experiment. Actually, the opportunity cost is pretty de minimis relative, or sorry, the discounting cost is de minimis relative to the opportunity cost. And so that's why I generally prefer putting in the opportunity cost. All right, last thing I will say, and then I will stop, is that you can distinguish between this jump and diffusion type models by looking at the actual time distribution of stopping. And it turns out that the diffusion model is mathematically equivalent to what psychologists call a DDM model, which is a model that they designed to explain stopping times. And so this is the other thing that Mike and I talk about. Here's some data from the kind of experiments that psychologists like to run. Someone is primed with a cue for what the right decision is, and then they make a decision. If the cue was good advice, they sort of are likely to make a good decision. And the distribution of stopping times is sort of unrelated to that. If the cue was bad advice and they stopped quickly, they're likely to make the wrong decision because they relied on the cue. Whereas if they take a long time, they are likely to make a better decision because that means they're thinking about it and didn't just go with the cue. And the point is that the jump model would be flat, step, flat. The diffusion model looks like this curve. And that's why we think the diffusion thing is a little bit more realistic. All right, so to conclude, there's a rich static and dynamic literature on rational inattention. There's also a huge literature on Bayesian dynamic persuasion that I haven't talked about at all. We know what happens when agents choose their own information now. We know what happens when they're being persuaded by a principle, but what we'll talk about next time is what happens when they're engaging with a principle who doesn't care what action they do, but just wants to keep them from stopping too early. And that'll be the subject of it. All right, so thank you.